Now let's see bond order. So here you are going to look at single, double and triple bonds. So single bonds, it involves one pair of electrons shared. As you can see here, this is representing 2 electrons, so one pair of electrons shared. This is 2 pairs of electrons shared, and this is 3 pairs of electrons shared. And the more the number of bonds, the closer the atoms get. So triple bonds hold atoms closest together. Double bonds hold it close together, and single bond hold it furthest apart. Now, the shorter the bonds, the stronger the bonds. So triple bond is stronger than double bond is stronger than single bond. And if you look in terms of bond length and bond strength, we can conclude that bond strength increase in this direction. So triple bond is the strongest bond, and you can see the bond enthalpy here. The bond enthalpy tells us about bond strength. So triple bond is the strongest bond. But if you look in terms of bond length, you can see this is the shortest bond. So if we go in this direction here, the bond length increases. Now, try to give a thought. How does the presence of double and triple bond in molecules influence their reactivity? This is one of the linking questions. Try to think how reactivity is affected by bond, the type of bond that is present. Let's now see the coordination bond. Now, a coordination bond is a special kind of bond in which one of the atoms that is involved in the covalent bond is going to donate both electrons to be shared. So normally in a normal covalent bond, you have one atom donates one electron and the other one donates an electron, so they share one pair of electron. But here only one of the atom is going to provide both electrons for sharing. Coordination bonds are indicated by an arrow along the bond. So for example, if oxygen is going to be donating electrons to carbon, so it's going to be shown like this. So you can have 2 normal covalent bonds and then 1 coordination bond. So it's going to be shown like this, where the direction of the arrow shows which atom donated the electron pairs. So it could be like this. And once formed, a dative bond or a coordination bond, so it's the same name for this type of bond. So it has the same characteristic as a normal covalent bond. So you cannot distinguish between the two, but it's just a little bit of difference between the two. So let's see how we form ammonium ion. This is an example where coordination bond happens. So you have NH3 that is going to bond with H+. So H+ is an atom which has lost all its electrons. So it doesn't have any electrons. So it is positively charged. So it has no electrons. Therefore, the nitrogen can bond with the hydrogen, whereby the nitrogen is giving both electrons to the hydrogen. So you end up with NH4 that looks like this. That can be represented like this. So this is the coordination bond here, which shows that nitrogen is providing both electrons in that special covalent bond. Similarly, for the formation of the hydronium ion, please correct this. So you have H2O. So H2O, which usually looks like this, and this is going to bond to H+. So similarly, H+ has no electrons. Therefore, the oxygen can donate its electrons to one of the hydrogen. So normally this is going to happen where one of the atom has lone pair of electrons that can be donated to another atom that has vacant orbitals. So take this down and you are going to try these reactions. So you have ammonia with boron trifluoride to form this compound. So try to do the chemical reaction where ammonia is NH3 and boron trifluoride is BF3. Try to do the reaction and draw the compound BF3NH3 where you have a coordination bond here. Similarly, between ammonia and beryllium difluoride, which looks like this. So boron here has vacant orbitals and beryllium has vacant orbitals. So try to do these coordination compounds. Pause the video and then you check your answer. So here you have the structure of NH3BF3. So this is a coordination bond. And over here you have the formation of two coordination bond between two NH3 and one BF2. And here you have the coordination bonds like this. Now try to form a dimer. A dimer means it contains two molecules. So when two molecules combine together, you have a dimer which is formed. So two AlCl3 molecules will combine by a coordination bond. So if you have two AlCl3, you can see that this one has a vacant orbital and this one has lone pairs that it can donate. So this one can donate to this Al, and here similarly this Cl can donate electrons to this Al. So you can have one coordination bond here and one coordination bond here. So you have a dimer which is formed, and we are going to draw it like this. So you can see you have a dimer which is formed where this Cl donates electrons to this aluminium and this Cl donates electrons to this aluminium. So these are the two coordination bonds. Now even for carbon monoxide, you have coordination bond which is formed. Now if you look at the Lewis structure of carbon monoxide, it would normally look like this, where you have your 5 electron pairs like this. But you can see here that carbon has an incomplete octet. So what happens that this is going to go here. Now when we do this, what is happening? So the oxygen is providing both electrons in the bond. So you end up with two normal covalent bonds and then one dative bond. So this is the structure of carbon monoxide with the coordination bond. Let's now see coordination bonds in transition metal complexes. This is HL. Now, transition metals, they can form complex ions. Like when we write FeH2O 6 times with a charge of +3, this is what we mean. This is the structure that happens. So the oxygen is forming coordination bond with iron. So there's 6 oxygen forming 6 coordination bonds with Fe3+, and this is how the structure looks like. And this is CuH2O 6 times. So you have oxygen donating lone pair of electrons to the copper. Now, these complex ions, they contain coordination bonds which hold together the central metal cation and surrounding atoms or groups of atoms called ligands. So the H2O here, this is called a ligand. You have many ligands that exist. NH3 is a ligand, so it has a lone pair. It can donate this lone pair. Cl is a ligand, so Cl minus is a ligand, so it has lone pairs. OH minus has lone pairs, it can donate. So ligands have a lone pair of electrons which can be used to form coordination bonds to the central metal ion. So I'm going to do one example. So you have Cu2 plus forming a complex with 4 Cl minus ligands. So Cu2 plus will have 4 Cl minus. So Cl minus, I'm going to exclude the charge here. Cl, Cl, and Cl. I'm not going to forget the lone pair of electrons on Cl minus here. So you have 4 Cl minus, 4 minus 1, and then you have Cu2 plus. So plus 2 minus 4 gives me minus 2. So overall charge will be 2 minus. So this is CuCl4, 2 minus. And this is called a complex compound, or in this case a complex ion. You're going to try to draw the complex ion formed with 4NH3 and 2H2O with cobalt 2 plus. Because you have 6 ligands here, so 2H2O and 4NH3, put the H2O on the 2 tops like this, and then you have the NH3 on the 4 sides like this. We are later going to do the shapes of these molecules, and then you will understand why we draw it like this. So this is going to be the last question for today.